Yes friends, how are you? How's your life going on? Today we are going to talk the structure of Corba or Corba architecture. Okay, so let's pay attention. Here we go. The OMG's Object Management Architecture, OMS stands for Object Management Architecture, tries to define the various high-level facilities that are necessary for distributed object-oriented computing. The core of the OMA is the Object Request Broker. ORB stands for what? Object Request Broker, a mechanism that provides object location transparency, communication and activation based on the OMA. The Corba specification, which provides a description of the interfaces and facilities that must be provided by compliant ORBs, was released. ORB is composed of 5 major components: ORB, ideal, dynamic invocation, interface repositories, and object adapters. These are discussed now. So the object request broker. The Corba specification must have software to implement it. The software that implements the Corba specification is called the ORB. The ORB, which is the heart of Corba. What? The ORB, which is the heart of the Corba, is responsible for all the mechanism required to perform these tasks. So now you can pay attention here. The structure of the Corba: client, object implementation, okay, dynamic invocation, client ideal, ORB interface, static ideal, skeletons, dynamic skeletons, object adapter, okay, and ORB core. See, prepare the object implementation to receive the request, communicate the data making up the request, okay. So figure shows a request being sent by a client to an object implementation. The client is the entity that wishes to perform an operation on the object, and the object implementation is the actual code and data that implements the object. Note that in this figure, the client, ORB, and object implementation are all on a single machine. There are two important things to note about the Corba architecture and its computing model. Both the client and the object implementation are isolated from the ORB by an ideal interface. All requests are managed by the ORB. This means that every invocation, whether it is local or remote of a Corba object, is passed to an ORB. In the case of a remote invocation, however, the invocation passed from the ORB of the client to the ORB of the object implementation. Okay. Next, here you can pay attention: a request from a client to an object implementation. Right. This diagram shows. Next, different vendors and different ORBs. See, since there is more than one Corba implementation and these implementations are from different vendors, a good question at this point would be whether objects implemented in different ORBs from different vendors would be able to communicate with each other. The answer is that all Corba 2.0 and above complaint ORBs are able to interoperate via the Internet Inter-ORB Protocol, or IIOP for short. This was not true for Corba 1.0 products. However, the whole purpose of IIOP is to ensure that your client will be able to communicate with a server written for a different ORB from a different vendor. Now, you can pay attention here: a request from a client to an object implementation within a network. Okay. Next, interface definition language, IDL. As with RMI, Corba objects are to be specified with interfaces which are the contract between the client and server. In Corba's case, however, interfaces are specified in the special definition language, IDL. The ideal defines the types of objects by defining their interfaces. An interface consists of a set of named operations and parameters to those operations. Note that ideal is used to describe interfaces only, not implementations. Despite the fact that ideal syntax is similar to C++ and Java, ideal is not a programming language. Through ideal, a particular object implementation tells its potentials clients what operations are available and how they should be invoked from ideal definitions. The Corba objects are mapped into different programming languages. Some of the programming languages with ideal mapping include C, C++, Java, Smalltalk, Lisp, and Python. Thus, once you define an interface to objects in ideal, you are free to implement the object using any suitable programming language that has ideal mapping. and, cons- and consequently, if you want to use that object, you can use any programming language to make remote requests to the object. Next, dynamic invocation interface. Invoking operations can be done through either static or dynamic interfaces. Static invocation interfaces are determined at compile time and they are presented to the client using stubs. The DII, the dynamic invocation interface, on the other hand, allows client applications to use server objects without knowing the type of those objects at compile time. It allows a client to obtain an instance of a Corba object and make invocations on that object by dynamically constructing requests. Dynamic invocation interface uses the interface repository to validate and retrieve the signature of the operation on which a request is made. Corba supports both the dynamic and the static invocation interfaces. Dynamic skeleton interface. Analogous to the DII is the server-side dynamic skeleton interface, which allows servers to be written without having skeletons or compile time knowledge for the objects being implemented. Unlike DII, which was part of the initial Corba specification, DSI was introduced in Corba 2.0. DSI, what is DSI? Dynamic Skeleton Interface. Its main purpose is to support the implementation of gateways between ORBs which utilize different communication protocols. However, DSI has many other applications besides interoperability. These applications include interactive software tools based on interpreters and distributed debuggers. Next, interface repository. IR. See, the IR provides another way to specify the interfaces to objects. Interfaces can be added to the interface repository service. Using the IR, a client should be able to locate an object that is unknown at compile time, find information about its interface, then build a request to be forwarded through the ORB. Next, object adapters. An object adapter is the primary way that an object implementation accesses services provided by the ORB. Such services include object reference generation and interpretation, method invocation, security of interactions, and object and implementation activation and deactivation. Next, let's move to Corba Rmi. See, RMI stands for Remote Method Invocation. Okay, RMI interface over the Internet Inter-ORB protocol, which delivers common object request broker architecture, distributed computing capabilities to the Java 2 platform. It is based on two specifications: the Java language mapping to OMG ITL and Corba IIOP 2.3.1. With features inherited from Corba, software components that work together can be written in multiple computer languages and run on multiple computers. In other words, it supports multiple platforms that can make remote procedure calls to execute, say, a subroutine on another computer as defined by RMI. The Java RMI IOP specification was created to simplify the development of Corba applications while preserving all major benefits. It was developed by Sun Microsystems and IBM, combining features of Java RMI technology with features of Corba technology. RMI IOP only uses the generated code for remote objects and does not require supplementary classes for non trivial data. As this is the case with Corba, this results in less code and a smaller footprint. RMI IOP is largely based on the object by value concept and serves as a container or direct replacement for Corba structure, unions, sequences, arrays, strings. No separate ITL is necessary. Instead, the data structure definition are supposed automatically collecting the necessary data via reflection mechanism. Both Corba and RMI IOP uses the same general inter ORB protocol communication standard if required. It is possible to generate the ideal definition for the involved RMI IOP data structures and use this definition to arrange the interoperability between the RMI IOP and plain Corba applications. The recent versions of RMI IOP derive their servants from the standard servant class, hence it is possible to connect them to the Corba ORB manually, involving, if necessary, the portable object adapter, portable interceptors, Corba naming service, and all other standard Corba features. So programming in a multi-language RMI system such as Corba Rmi requires more of the programmer than programming in a single language RMI system such as Java Rmi. So the following concepts are used: the object model offered by Corba, the interface definition language and its mapping onto the implementation language. In general, the programmer defines remote interfaces for the remote object and then uses an interface compiler to produce the proxies and skeleton. But in Corba, proxies are generated in the client language and skeleton in the server language. Next, Corba's object model. In this model, client is any program that sends request message to remote object and receives reply. The term Corba object is used to refer to remote object. A Corba object implements an ideal interface, has a remote object reference, and is able to respond to invocations of methods in its ideal interface. A Corba object is not implemented by a language which is not object-oriented language, since implementation languages will have different notions of class or even none at all. Therefore, classes cannot be defined in Corba ideal, which means that instances of classes can't be passed. Data structures of various types and arbitrary complexity can be passed as argument. So friends, today we discussed about structure of Corba and some part of Corba RMI, right? In structure, it was the structure, okay, of Corba 2.0, right? We discussed the object request broker, different vendors and different ORBs, interface definition language, dynamic invocation interface, dynamic skeletal interface, interface repository, object adapters, and a small part of Corba RMI. So that's all for today. I hope you must have got knowledge. Thank you very much.